Hello everyone, I'm Sindhu Hegde. I'll be presenting our work on understanding co-speech gestures in the wild. Understanding human communication has been one of the crucial goals of AI. Let us watch a quick video to learn more.
Is beautiful.
Here, the lady is communicating with speech. She has a very distinct facial expression, and of course, there is the corresponding text. And today, there are models like Siri and ChatGPT, which are very advanced in these modalities. However, human communication is not limited to speech and text. Nonverbal communication is a major part because humans gesture when speaking. And compared to other modalities, research in gestures is quite limited. That is the focus of this work here, where we aim to build foundational models for co-speech gestures. Studying co-speech gestures comes with numerous challenges, like there is no direct one-to-one mapping that exists between gestures and words. Like the same word, zoom in this example, can be gestured in very different ways. And there could also be similar gestures belonging to completely different words. In addition, there could also be random gestures which are unrelated to what is being spoken or no gestures at all. Addressing these challenges is a key to develop gesture-based models. In this work, we learn a joint embedding space with the three modalities, gestures, audio, and language, such that the matching components, like similar gestures and their corresponding speech and text, are clustered together in this embedding space, and the non-matching parts are pushed apart. To do this, we designed JGAL, a weakly supervised model. An overview is shown here. There are three modality-specific transformer-based encoders for the three inputs. Text and audio form the content part, so they are fused together. Now, we have the gesture embeddings and the content embeddings. The training is done with two losses. The first one is the phrase contrastive loss, where the objective is to learn the global gesture and content correspondences. And the second one is gesture word coupling loss, where the aim is to learn the fine-grained word level correspondences. More details can be found in our paper. Coming to the datasets part, the model is trained using two public datasets. The first one is SPATS and the second one is multi-VSR. And together, they form around 718 hours of data. For testing, there are no labeled datasets available. Thus, we annotate three new testing benchmarks for the three different tasks. The details will be explained soon. So, we evaluate the learned representations from our model with three different tasks. Let us start with the first task of gesture word spotting. Here, the task is, given a sentence and a speaker video, we want to localize where exactly the gesture occurs in that video. The newly curated dataset for this task is called AVS Spot, which has a diverse set of speakers with 500 videos in total. Some of the examples of the datasets are shown here.
Back in the 1300s, it meant
four really cool segments.
Light travels in straight lines.
So every video in our dataset has these unique keywords which are gestured well. Some more examples are shown here. All right, so this is one of the results from our model.
Your presence in terms of your energy. You need to.
The keyword here is energy. We can see that when the person speaks and gestures energy, the heat map shows a very high similarity score, which is indicated by red color in the heat map. So this says that when is that word gestured in the video. The second task is cross-model retrieval. This is a standard retrieval task where, given a speech or text query and a database of gestures, the aim is to retrieve top K matching gestures. For this task, AVS RIT is our new evaluation dataset. One of the results from our model is shown here. The query here is content and future is the keyword to focus. And we can see that in the retrieved gesture videos, all of them match the semantics of future, which is like a forward pointing gesture. And the final task is active speaker detection. So here, given a scene with multiple speakers, the goal is to predict who is the active speaker. We create AVS AST as the test dataset, where we consider up to 5 negative speakers for evaluation. One of the results is shown here.
Beginning of December. So yeah, very clever machine.
So an interesting point to note here is that the speakers are wearing masks, and the traditional active speaker detection methods fail for this example because they all rely on lip synchronization signals. Our method instead relies on gestures and can work well for such extreme cases. That was all about our work. Thank you for listening. Please visit our webpage. The trained models, code, and datasets have been released. Thank you.